Hello, Varun. Are you there? Hello. Good evening, Varun. Shall we start the class? Hello. Hello. Varun. What are you doing, man? After logging in, you are watching something else? Varun? Hello. Yeah, what happened? Now only you are hearing? No, you were watching something else, I think. Is it? Were you watching something other? Something else in the... Then? You are looking at the monitor, but I have been waiting for some time. You are not responding. Shall we start the class? But I am able to see you. Okay, right. In the last class, I asked you about the density, isn't it? The mass density. You know the formula for density. Okay, now it's okay, isn't it? Let's just continue. So, yesterday I asked you mass density, isn't it? So, formula for density. Density is equal to mass by volume, m by v, we know that. So, that is actually called a mass density, right? What do you understand from that? It is, from the table, the tabular column we have seen, we are classifying this into two categories. One is optically denser, or on the basis of mass, whether it is, we are talking about density. It means that, I asked you at the last end of the session, I asked you, and when you compare the water and kerosene's density is lesser. Water density is more than kerosene. That is why when you pour kerosene in water, the kerosene will float on the water. That shows that it has got less mass density. But when you compare the optical activity, right, that is refractive index, it has got more density. That means it will not allow light to easily pass through that. That is, when light travels in water and light travels in kerosene, the speed of light in kerosene will be lesser. Right? So that's what we say, that it doesn't mean, from the table you have seen that an optically denser medium may not possess greater mass density. When you compare the kerosene has got a more refractive index, but mass density is lesser. That is what the point says, that an optically denser medium means the refractive index is more. Refractive index is more. You can see that the previous tabular column you have seen that kerosene has got 1.44, but water has got 1.33. That means we know that formula, refractive index is equal to velocity of light in vacuum by velocity of light in medium, isn't it? So when can you get this value? It means that this, when refractive index is more, what do you understand from that? What do you understand from that? The velocity of light in air is more, in that particular material is lesser. That means in kerosene the velocity of light is reduced. It shows that optically kerosene is denser. Optically kerosene is denser. But mass wise, if you look at that, it is less density when compared with the water. You understand? That is the point you have to remember here. This is what we are talking about. Okay, kerosene having higher refractive index is optically denser than water, but the mass density is less than water. Okay, this may be, sometimes they may ask in the multiple choice. So that is what the point says. Okay, so the ability of a medium to refract light can also be expressed in terms of optical density. So far, based on the refractive index we have spoken. So based on optical density, we can say whether the medium will be able to refract light. But this, when you talk about optical density, it has got a definite connotation. That is, it has got a abstract definition, exact definition. It is not same as the mass density. Simply if we say optical density, we cannot say it is mass density. It is different from mass density. Okay, so far we have seen about a rarer medium and a denser medium, isn't it? It is depending upon in which the light is traveling faster or slower. Depending upon that, we can say that medium is optically denser than the other. Okay, so that we say rarer or denser. If it has got less density, less optical density, we say rarer medium. If it has got more density, we say denser medium. Okay, depending upon that optical density, we can say about that. Yeah. So when you compare, when you take any two media like air and or vacuum and glass, or water and air, okay, so one with the larger refractive index is optically denser. Optically denser. If the refractive index is more, it is optically denser. Can you tell me why? Can you tell me why? Very good. Good answer. When you say refractive index is more, it is optically denser. Why do you say? Because optically denser means the light cannot travel fast with a higher speed, with high velocity. That's what it says. That is, the density is not allowing the light to pass through as it is traveling in air. So that way, when you say that, say for example, the refractive index of kerosene is 1.44. See, 1.44. For kerosene it is 1.44 refractive index, right? So what does it mean? This is what we call as refractive index. We say that it is C by V, or we can say the velocity of light in air to the velocity of light in the medium, right? So when can you get this more than 1? That means this should be greater. That is, C is greater than V. Then only we can get 1.44. Or otherwise, V is lesser than, we say V is lesser than C. V is less velocity. So when can you say that velocity of light is less than the velocity of light in air? That means the medium is not allowing, it has got more density. So by the term 1.44, by looking at the refractive index, if it is more than water, that means that the material, the kerosene, is optically denser than water. Optically denser than water. Okay, this is what it says. Right. So similarly, if you say 1.33 for water means, for 1.33 means, when you compare the velocity of light in water and velocity of light in kerosene, kerosene is optically denser. Optically denser. Water is optically rarer medium when compared to kerosene. So that is what we have to understand. Okay. Right. So one is optically denser, other one is lower refractive index, optically rarer medium. Rarer and denser. These are the two important points we have to understand. So in rarer medium, it means that the speed of light is higher always. The light can travel at a high speed with the maximum speed in a rarer medium than in a denser medium. Okay. So that means when light is traveling in denser medium, when it is slowing down, when the velocity is brought down, naturally what will happen? It will bend towards the normal. As we have seen in the video, how the truck is traveling from a main road to the marshy road or sandy soil. The tire is traveling, the wheel will bend and turns, isn't it? In the similar way, when the light is traveling from air to denser medium, due to the change in the velocity, change in the speed, it will be bending. The light wave will bend towards the normal. Okay, remember that. At this point you have to note down, when it is traveling from a rarer medium to the denser, it is bending towards the normal. This point you have to note down, towards. It is traveling towards the normal. Right? And similarly, when it is traveling from denser to the rarer, it bends away from the normal. It bends away from the normal. Isn't it? So we have seen that in the glass slab experiment. In the glass slab, right? When you are drawing, this is the normal. This is the normal, and the light ray is incident like this. Actually what happens? It is rarer. First it is rarer, and the second one is denser. Isn't it? So if it is so, it will bend away from the normal. It is not going towards that, so it will away from the normal. That means it is actually bending. Okay? So this is what it means. So it means that it is away from the normal. Okay? So if it is in the other case, it will be towards the normal. So in the multiple choice question, they may ask, when it is traveling from rarer to denser, whether it is towards the normal or away from the normal. This is the meaning it reveals. Okay, next, as we have seen about the refraction of light by spherical mirrors, we are going to learn about the refraction by spherical lenses. Okay, first of all, we have to see what is a lens. In our day-to-day life, we have been seeing that people are wearing spectacle for reading, and even the watchmakers, those who are repairing the watches, they use this a small magnifying glass. They'll keep that in the eye and look at the watch so that it will be looking bigger to magnify the internal parts, isn't it? So these are the. Have you ever seen that this magnifying lens we used to read? The astrologers, they used to see the palm reading, isn't it? They will have a glass in their hand and they'll use that. Have you ever touched that surface, how it is? Whether it is plain or curved, it will be like a thicker in the middle and thinner at the edges, isn't it? All these are nothing but examples for lenses. So, on the contrary to that mirror, what is that lens? How is it going to bend light? That is what we are going to learn in detail in this session. Okay. So how to define a lens? A lens is nothing but a transparent material bound by two surfaces. A transparent material. Here you have noted down the word transparent, but in the mirror it is not transparent. In the mirror, one side it is coated with a reflecting surface, isn't it? Reflecting material. But here, both sides it is not coated, it is transparent one, bound by two surfaces, of which one or both surfaces are spherical. That means one can be a plane one can be a spherical one, or both can be plane. If both cannot be plane, one can be plane or other can be bent, or both can be bent. That forms a lens. Here, it should be at least bound by one spherical surface. If it is bound by one spherical surface, in such cases, the other definitely would be a plane one. Other would be a plane one. Here you can see that these are all the examples for lenses. Suppose a lens has got two spherical surfaces, which is bulging outward on both the sides. Such lens is called a double convex lens. You can see that it is bulging on both sides, back side and front side. That is like this way. It is bulging like this. So these kind of lenses, on both the sides it is bulging outside. It is called double convex. You know that if it is curved outward, it is called a convex, isn't it? It is when it is curved outward, it is called a convex. So since it is curved on both the sides, it is called a double convex, or simply we say convex lens. So convex lens means on both sides should be curved, both sides should be bulging. It should be thicker in the middle and compared to the edges, right? And this convex lens always converges light rays. It will always converge the light rays. When you are learning about lenses, you have to forget about the mirrors. Never have confusion with the mirror and lenses. I'll tell you. Okay, don't have confusion with the mirror and the lenses. You have to forget it. Now this is a new chapter. Things will be different. So a convex lens will converge the light rays. So that is why a convex lens is always called a converging lens. It is called a converging lens. And a double concave lens. There is another one. Here it is, so far we have seen double convex. There is another one called a double concave lens, which is bound by two spherical surfaces curved inward. Curved inward. It is thicker edges than like both sides it is curved inside like this. These are called a double concave, we say. Double concave, or simply we call it as concave lens. So when you say concave lens means it has got two spherical surfaces which is curved inward. So this is double concave. The previous one was double convex lens. Okay, these are available in the market easily. You can purchase and do the experiment using a candle at your own house also. It will be very interesting to note down. The mirrors, the lenses, they are all available in the shops, in the scientific suppliers. Since you are in Tirupur, it is readily available in Coimbatore. You can just refer any one of the shops in Coimbatore and ask them to send it through courier also, they will send it. You can pay it. So that way you can perform the experiments at home also. It will be interesting to note down. Okay, now a lens has got two spherical surfaces. So when you say two spherical surfaces, this is only a part of the sphere, whole sphere. Suppose in the beginning also, when you are talking about mirror also we have seen. Here also, so here also this is a spherical surface which is made up of a glass, like a, you can consider this like a solid glass, a solid glass. You can cut one part here. If you cut one part like this, that will be a plano-convex. One side will be plane. You asked me, no, if one side, if it is a plane one, if it is other side, if it is bulged one, it is called a plano-convex. Or sometimes one will be like this, the other one will be like this. It is called a plano-concave. Plano-convex and a plano-concave. These are the two lenses. But whatever be the lens, definitely it is forming a part of that. So this is forming a part of a sphere, and that sphere has called a center point, and that is called the center of curvature of the lens. Okay, so what you have to see, a lens has got two spherical surfaces. Each of these surfaces forms a part. You can see that this has got two center of curvature. This side you can draw a circle, and this side also you can draw a circle, and both has got a center of curvature. Okay, do you understand? And usually when they make this, they will take care that on both the sides the center of curvature is same, because if it is not properly curved, the center of curvature will be changing. When you change the glass on the other side, readings will be different. So they will take utmost care that the center of curvature, the radius of curvature for both the sides will be same. So if the center of curvature is usually represented by letter C, as we have seen in the mirror also, center of curvature of a mirror, here also center of curvature of a lens. And we have seen that a lens has got two spherical surfaces. So for each spherical surface, as I said, it has got one center of curvature. So we call this as C1 and C2. In front of the mirror, in front of the lens, we call it as center of curvature, first one. Behind this mirror, it is called a C2, C1 and C2. So for making references, we will be using this when you are drawing the ray diagrams. Okay, C1 and C2 for both convex and the concave lenses. Both lenses will have C1 and C2. And a line, imaginary straight line, which is passing through both these center of curvature C1 and C2 is called the principal axis. For mirror, we say that a line which is passing through the pole of the mirror, center of curvature and pole of the mirror, that is called a principal axis. Here, the line should pass through the center of curvature of the lens, that is called a principal axis. And similarly, the central point for a mirror, it is called a pole, but here for lens it is called optical center, optic center or optical center, and it is represented by O. For mirror it is P, pole, here it is O. So if any ray which is passing through the optical center of the lens will pass through the lens without any deviation, You may ask, why sir? Why is it passing through that without any deviation? Because it is at this point there is no curving. So only curved surface will be diverging or converging. Curved surface only will be diverging or converging. Since at this point O, it is a flat surface, so the light ray will go without suffering any deviation. Okay, so the ray passing through the principal axis, optic center, okay, will pass through without any deviation. You have to remember that one. And the effective diameter of the circular outline of a spherical lens is called aperture. As you have seen for the mirror also, the external diameter, that is called the aperture. Similarly here also, the effective diameter of the circular outline is called the aperture. You can see that there are different lenses which we use for camera for different aperture. So depending upon the aperture, the photo clarity will also be different. Okay, so aperture is nothing but the effective diameter of the circular outline of the spherical lens. Circular outline of the spherical lens, this part, this is called the aperture. Okay, right. Now, as we have performed in the beginning using a mirror also, we can perform some activities using the lenses. Like you can just take a double convex lens, or simply call as convex lens, and show that directly to the sun. Okay, and after that the sun rays coming from the sun should fall on the lens, this lens, and through that lens we say that it is a converging lens. So all the rays which is coming from infinite distance, after falling on this, they will be converging at one point. At that point, if you keep any material, because of the heat rays, when you are converging, it will get burnt. So such a simple experiment here, you can just see that using a video also, which will be very interesting to note, right? Look at that video. Here you can see they are using a lens for heating the paper. there is a black paper here which is burning quickly. So we say that when the light is coming from a infinite distance, that is from the sun, it is assumed that they are parallel rays, which is parallel to the principal axis of the lens. So when it is parallel to the principal axis, we have seen in the mirror also, they will be converging at one point, which is called a principal focus. Similarly, here also, when they are converging at this principal focus, at that point if you keep any material, definitely they will be getting burnt. You can see that they are focusing, that focusing point, that point is nothing but called the principal focus. You can see if it is left for some time, it will simply burn the paper. At that point, by mistake, if that spot falls on your hand will also be burnt. That much hot it will be. Right? Similarly, you can see another video also later, but just as I have told you, the rays which is coming from the sun, which is far from a distance, can be considered as a parallel rays. When these parallel rays, you can see that again, the rays, how they are converging. They are parallel rays, they are converging at one point. Right? So, when these several rays of parallel light rays, when they are parallel to the principal axis, after falling on this convex lens or converging lens, after refraction, you have to say after refraction, this phenomena is important. They are converging at one point, which is called a principal axis. On the principal axis, at one point they are converging. At that point, we name this as principal focus, which is called a F1 or F2. Here we are taking two principal focus, because since lens has got both sides, it is curved outward. We can keep the lens on both the sides. You can turn that upside down, so that in one side, if the rays are coming to the left hand side to the right hand side, left hand side is F1 and right hand side is F2. Usually we say like this. So this is first principal axis and this is another principal axis. On either way, we can take the light rays coming from and falling on the lens. Right? So the next one, similarly, if it is a double concave or simply concave lens, when several rays of light parallel to the principal axis are falling on a concave lens, what will happen? After refraction from the lens, they appear to diverge from a point on the principal axis. Here you can see, after falling there, after refraction, actually if it is converging lens, they will focus at one point, principal focus. But here it is diverging lens, so they will get diverged, and when you extend this point, that point is nothing but called the principal focus. They appear to diverge from the point on the principal axis. That point is nothing but called the principal focus of the concave lens. Right. The next one is, if you pass parallel rays from opposite surface of the lens, as I have told you already, F1 and F2, two principal focuses, foci we can say. When you say principal focus, it is singular. Principal foci means plural. Right. So as I said, on both the sides, it is usually represent the principal focus. Since it has got two spherical surfaces, they are represented as F1 and F2 on either side. Okay. And the distance, we know that from the principal focus to the optic center, that is nothing but called the focal length of the lens. The letter small f is used to represent this principal, that is focal length. It can be measured on either side. Wherever you are getting the image, from that spot to the center of the lens, what you call it as the optic center. From that to that, this distance is nothing but the focal length of the lens. It can be easily measured, because these kind of lenses will easily form the image. When you take a long distance tree, which is at a far distance, focus that and keep a white paper behind that, that image of the tree will be seen on the paper easily. So where you are getting the clear image, from that point, from the screen to the lens, if you measure, that is nothing but called a focal length of the lens. Right. So now we will see how the images are formed by using this convex, that is convex lens. First we will see convex lens, then we will see concave lens. Now, Usually we say we represent this formation of image formation by convex lens by using a ray diagram. Because it is useful for us. Already we have learned that it is useful for us to locate the position, nature and the size, relative size of the image, so that we use that for representing. Now let us see the first point. This is similar to the mirror, right? The basic points we have understood. 4 points we have studied in when we are talking about a mirror, the image formation. Based on that only we'll see, we'll take any 2 rays and form that, isn't it? Here also, when a ray from the object which is parallel to the principal axis, right, after refraction what will happen? They will pass through the principal focus on the other side of the lens, right? Similarly, in case of concave lens, they will appear to diverge from the lens on the other side. You have to see on the other side, but here it is on the other side, but here it is on the same side. For concave, it is appear to diverge from the same side. Look at that animation. So it is parallel, it is passing through the principal focus, and when it is parallel, it appears to diverge from the principal focus on the same side. Okay, right. Similarly, a ray of light which is passing through the principal focus, okay, which is passing through this principal focus, after refraction will emerge parallel to the principal axis. After refraction from the convex lens will emerge parallel to the principal axis. And similarly, a ray of light appearing to meet at the principal focus, after refraction will emerge parallel. It is opposite to that. You can see that how it is, which is passing through the principal focus. Okay. After refraction, it is opposite to the previous one. Where it is parallel, it is passing through the principal focus. If it is through the principal focus, it is parallel. It is emerging parallel. And similarly, when it is directed towards the principal focus, okay, a ray of light appearing to meet or directed towards the principal focus, after refraction, what will happen? After refraction, it will simply pass through the parallel to the principal axis, right? So this is quite opposite to the previous point. So you have to remember that. And third point, a ray of light passing through the optic center will emerge without any deviation. Already we have studied, if it is passing the principal focus, that is optic center, this way or this way, if it is through the optic center, it will not suffer any deviation, whether it is in this angle or this angle, whatever be the angle, it will be passing through that without any deviation. That is the third point you have to remember. Now based on that, we are going to see by keeping the object in different locations and draw the ray diagram, and finally we will tabulate that. Okay, so take the first one. At infinite, it is something like a sun rays falling from the infinite distance on the lens. So what will happen? Naturally, when they are parallel to the principal axis, after falling on the lens, after refraction, they will meet at one point, which is principal focus. So the position of the image is at principal focus, and highly diminished image. As we have seen that when you are focusing the sunlight, it is like a spot, bright spot, isn't it? So it is diminished, highly diminished and point sized, because it is at a point, and real and inverted, because you are able to catch that point on the screen. So it is a real one and a inverted one. Instead of a sun, if you take any tree, the tree image can be caught on this point. It will be inverted and very, very small, diminished one, point sized. Okay, this is the first point for infinite distance, at infinity. Okay, let us take the second one. Beyond 2f. What is meant by beyond 2f? Tell me, Varun. What do you mean by beyond 2f? What is meant by that? Beyond C, or otherwise, in otherwise, what can you say? What is this value called? What is this value called? No. What is this actually called? From point O to C1. What is it called? Yes? Karthik. This is nothing but the radius of curvature, isn't it? From center of curvature to the optic center, what is it called? Radius of curvature. Yes. So, beyond radius of curvature you can say, or twice the principal focus. Twice the principal focus, we can say, isn't it? So, beyond f means between this one. Beyond 2f means after the radius, okay, after the radius of curvature. So, if it is beyond this 2f means beyond C or beyond R, radius of curvature. So, what will happen? Where the image will be formed, it will be between f and 2f. Yes. So, the image will be formed between f and C. F and 2f we say. 2f is nothing but C. Either you can say C2 or 2f2. Because we are talking about the other side, actually we have to say between principal focus and twice the principal focus, or C. Okay, 2f. It is called 2f. This point C, otherwise called 2f, and this is f. So the image will be formed between f and 2f. F and 2f. When it is beyond 2f. You can remember by letter itself. 2f means how to draw. Very simple. We are taking image. We are taking two rays which is passing through the optic center, which is parallel to the optic center. Two rays we are taking. Right. So what is the procedure? When any ray is passing through the optic center, it will not suffer any deviation. One ray, that's all. Straight away you draw. Straight from here to here you draw that. Straight line. What is the second condition? This principal, this line which is parallel to the principal focus will usually pass through the principal focus. So you draw this one through the principal focus. Now when they are intersecting at this point you draw a line, that's all. Image formation. Naturally this line, this will be forming between f and 2f. Very simple. That is why I said before learning this, we have learned the basic concept. What is parallel means, where it will merge, where we will get that, isn't it? So based on that only we are applying this. Have you understood this now? Yeah. Now let us take the next one. When it is at 2f. Now we have taken beyond 2f. Now it is at 2f. At 2f means it is nothing but at center of curvature. At the center of curvature. So when it is at 2f, the image will also be at 2f only. Image will also be at 2f. Okay. So how to draw from this center of curvature? Draw a line. This is object AB. This is the object. Similar to the previous one, take a line, a ray which is passing through the optic center straight away, which is passing without any deviation. The other one parallel to the principal axis, again it will be passing through the principal focus. Now when you see that it is intersecting, that point will definitely be the center of curvature. At what distance it is here, the same distance will be there. Okay, right? So when the object is placed at a distance which is equal to the radius of curvature of the lens, the image will also be formed behind the lens at a distance which is equal to the radius of curvature of the lens. That is what the point says. When it is at 2f, image is also 2f, the image size will also be same, image will be real because you are able to get on the screen, but it is inverted because when it is kept here the rays are like this, so it is emerging and intersecting below the line. So when it is below the line it is inverted. That is all. Above the line means it is erect. Below the line means it is inverted. So easily we can draw the diagram. Very simple one. Similarly, third one. Now we have moved further from 2f, we have moved further in between center of curvature and the principal focus, between C and F, or we can say F and 2f, both are same only, between 2f and F, right? This is quite opposite to the previous, the first one. See that when it is beyond 2f, that is what it says, isn't it? Beyond 2f means, earlier we have seen that between f and 2f. Do you remember that first point? I'll just show you the first point. You look at that. See here, beyond 2f we have taken, the image is at between f2 and f and 2f, in between. Now you take the reverse of that. Now look at that. Okay, reverse of that. So the image is got beyond 2f, but here object is kept between f and 2f. That is what is between f and 2f. The position of the image will be beyond 2f, and since it is bigger one in size, enlarged one, since it is below the line, it is inverted. Do you get the point what I say? You can just pair it up. 2 points will be opposite to the other one. Do you understand? Yeah? The next one, at the principal focus. Now we have further moved. We have kept already between 2f and f. Now exactly at f. When it is at f, we cannot get the image, because this is the opposite of the first point. In the first point we saw that when the rays are from the infinite distance, the image is formed at the principal focus. Now when the object is at principal focus, image will be formed at the infinite distance, opposite to that. Now see, we are taking two rays, one is to the optic center parallel, now it is passing through the principal focus, and this is here passing through that. It will keep on going, they will never intersect. It means that it is understood that the image formation will be at a infinite distance. It will never coincide, that is coincide. They will never intersect. So we assume that they will meet at an infinite distance. So this is the opposite of the first point. So what is the point here? At the principal focus, the image formation is at infinity. Since it is going to meet at a different position, that is infinite distance, we can say that the image size will be infinitely enlarged, highly enlarged. You can say infinitely large or highly enlarged, and it will be a real image, and since it is below the line axis, it is a inverted one. So these are the points we have to sum up here now. Now the last one, sixth point is, again beyond this f, in between f and o. This is the last sixth point. Between f and o, principal focus and the optic center, the object is here. When it is brought here, the image will be on the same side. Image will be on the same side. Why? Because here when you take this object, it is, one ray is taken as if it is passing through the optic center, another one is parallel, and since here it is, you can see that very small part of this lens is taken, right? So here, after reflection, when it is parallel, it will pass through the principal focus. Now they are somewhat angular, isn't it? They are deviating, oblique at an angle. So when you extend this line, they will meet at one point on the same side of the lens. At that point, if you draw a line, that will be bigger than the object. The size of this image will be bigger than that. Since above the line it is a real one, it is erect one, and very, very large, enlarged. Where is it formed? It is formed on the same side of the lens. You need not locate that. You have to keep on moving the screen. At one point, we can get the image of the object, right? So these are the 6 points which is summed up here. You can just recollect it. What are the points? At the infinity, it is at the focus and highly diminished and point sized and real and inverted. So here it is at infinity, right? And compared to that, this is the next one. Okay, you can see that infinity object. The image is at focus f2. Now see that at focus object the image is at infinity. Both are interlinked. You can see that these two are interlinked. Okay, this one and this one opposite, that easily you can remember, right? And here highly diminished and point sized, here opposite are infinitely large and highly enlarged. Okay, both of them are real and inverted because they are on the other side, which can be below the axis, principal axis. So this point and this point both are same but opposite to that. And the next one is beyond 2f. When it is beyond 2f, the position of the image is between f2 and 2f2. Okay, f1 beyond 2f1 means beyond the radius of curvature. Okay, between f2 and 2f2. Diminished and real and inverted. Diminished, real and inverted. Right? So now we can compare this with the next one. What is that? The next one, this one and this one, both are same, you can see. When it is object, position of the object is beyond 2f1, f2 and 2f2. Now when the object is at f1, 2f, these two are interlinked. Okay, and this one and this one. By this way you can pair it and easily remember. Okay, you can just beyond 2f, between f and 2f, between f and 2f, beyond 2f. Here it is diminished means it is opposite, enlarged, but both are real and inverted. Very simply, you can just, if you write one, the other one will be easy. Now the next one at 2f2. This is at 2f2 means similar. There is no pair for this. At 2f1, at 2f, same size, real and inverted. Okay, the last one is between focus and optic center. Okay, this is special case. These two are special case. Between f and especially this one is special case because in this only we are getting a erect image and virtual one. All the other things are real. This is only virtual because virtual which cannot be caught on the screen. It will be keep on. You have to locate, but you cannot locate because you cannot get that on the screen. In front of the lens only we have to get that. Okay, so that is only it is virtual. And since it is on the same side above the principal axis, this is the real one and highly enlarged one. This is the special case. So these are the 6 points which you have to remember regarding the image formation by the convex lens. Okay. So remaining we will see in the next class. In the meantime, you keep practicing this ray diagram because this ray diagram is very essential. That by using this only by practice only you will be able to locate the position of the image. And in the exam also, quite often they will just give you the ray diagram and ask you to complete. Simply they will ask you to complete. What will they give? They will give one lens. They will see they will show you the object position, and they will ask you to complete the ray diagram. So for which you have to keep practicing. What is the position of the object? If the object is at this point, where the image will be, nature of the image, size of the image, all those things you have to keep practicing. Then only such kind of questions will be easier for you to answer. And also remember the difference between the lens and the mirror. Never have the confusion, because sometimes in the exam you may get confused and draw the ray diagram which is meant for a mirror. That should not be. So practice it very well, and the remaining we will see in the next class. Right. Thank you. Varun? Are you following, Arun? Hello? Hello? Arun? It's clearly shows that you are doing some more work.